and this is my screen. Hold on. Let me pull up the PowerPoint. Right. Okay, it's loading. Okay, there it is. All right, so I'm going to start screen sharing, and if you can see the screen, say yes. If you cannot see the screen, say no. So you can see the PowerPoint here. This is lesson 7.1, which is on systems of equations. So in this unit, we are going to talk about matrices and linear programming, which is very important. So matrices is a way to solve linear equations or systems of linear equations, but it is also part of a very broader field, which is called linear algebra, which you will use in college probably if you take mathematics a lot, and is very important for like data analysis as well as other scientific fields. So matrices. And also for linear programming, which is basically modeling real life situations with systems of equations and matrices. So those are some pretty important things that we're going to be learning within this unit about systems of linear equations. But these first two lessons will not be so complicated or deep. It'll just be a review, a more in-depth review and extension of linear systems. So today we're just going to go over linear systems again, in case you guys forgot, right? Okay, so let's start with the homework first from last time. This was about logarithms and stuff. And basically, you need to graph these, right? So graph, right? Last lesson was on graphing. So graph these, and then we can go over it in a couple of minutes. Right. All right, so let's go over this one. Who can volunteer on how to graph this? Does anybody know how to graph this? How about Kaylee? Kaylee, do you know how to graph this?
Not really.
Okay, let's walk through this. So what type of equation is this? Is this exponential or a logarithmic?
Exponential.
Right. So what does that look like? That looks like something like this, right?
Yeah.
And it passes through which point? What is the reference point here?
0, comma 1.
Yeah, 0, comma 1, because anything that like anything to the 0th power is equal to 1. So therefore that is the reference point. Whenever x is equal to 0, the x1 is equal to 0, then it's going to be equal to 1. All right, so to find where this new reference point is, we got to do some couple of things. And one of those is to basically find when this exponent is equal to 0, right? So you see this exponent right here, right? To find the new x coordinate of the reference point, which is basically how you graph it, you gotta set this equal to 0. So when is this equal to 0? It's when x is equal to -1. So our new reference point, because there are no y coordinate changes, is going to be -1, 1, right? And this makes sense because usually the function transformation of x plus 1 moves it to the left by 1. So that makes sense. Also, there are some things here, which is you're going to stretch it by a factor of 2. That isn't super important here, but if you do want to graph some points, you can. So why don't we just do that and graph some points? So we know the main idea, which is the reference point, right? Which is -1 and 1 here. So this is the reference point. Of course, it's still going to be opening up to the, well, the long side, the high side is going to be to the right. It was never like um it was never like reflected. So yeah, it'll still be similar to this parent graph right here, except it's going to be skinnier up high, right? Because it is stretched by a factor of 2. So if you put in some points here, for example, if we have x is equal to 0, y is going to be equal to 2 times 3 to the 1, which is equal to 6. So something like this, right? And you see the horizontal asymptote is still there because, again, there are no y changes, no y coordinate changes or shifts, right? So it's just going to be skinnier like this. And this is the y. This is the horizontal asymptote right here. This is y is equal to 0. So sometimes in some textbooks, when you see an asymptote, it's going to be a dotted line. But recently I found out that it's more helpful to visualize if you do a squiggly line like this. Of course, it doesn't look too professional. But usually in textbooks, it does give you a dashed line. But right now, when you're learning, just use a squiggly line because it's easier to visualize and it's just more simple, right? Because if you use a dotted line, you can't the 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 axis covers it up anyways. And it's very important to notice that the x-axis is an asymptote, not just an axis, right? All right. So now let's go on to the second graph here, and this is also an exponential function. Third graph, I think, is logarithmic. So yeah, this one is not too hard. So yeah, give it a go for a couple minutes, and then I'll come back and do it. Okay, so let's go over this again. So who else can help this time? How about Jenny? Jenny, can you help graph this or not? Okay, how about Dan Lu? Dan Lu, can you come help and graph this?
Yeah,
All right, so first of all, which kind of function is this? Is this exponential or logarithmic?
exponential.
Right, so exponential, again, pull up the parent graph here. This is 1, 0, or no, not 1, 0. This is 0, 1, 0, 1 here, and this is the reference graph with the horizontal asymptote in the x-axis, something like this, right? So we know it's going to be looking something like that, right? Okay, so we have a couple of transformations here. Couple of transformations.
We
Number
shift
one,
it to the right by 2 units and down by 1 unit.
that's very good, very good. So our first transformation is, of course, x minus 2. And when we set that equal to 0, we know that the new reference point is going to be 2. Well, the x-coordinate of the new reference point, and then the y-coordinate is going to be -1, right? So now we can actually graph this. The x-coordinate is 2, and it's -1. So this is now the reference point here. And oh wait, no, it's not. The y coordinate is still 0 actually, because it used to be 1, so now it's 0. The -1 actually pertains to the horizontal asymptote, which you can see with this dotted line here, or squiggly line, whatever you prefer. And yeah, that is what happens, and that's about it. There's no actual stretches or compressions with this one. So the 2 right here doesn't actually do anything. That's actually just the base, so it doesn't matter. But there's no compressions or stretches, so it's just a bunch of vertical and horizontal shifts. So this one is pretty easy too. Just make sure the main idea is the reference point, right? The reference point, you gotta have the coordinates of the reference point. So now let's go on to some homework here. Number 3, y is equal to log base 2 of x minus 1 plus 4. So yeah, I'll give you a couple moments to do this. All right, so let's go over this one. All right, so I'm just gonna walk through this one real quick. So we have a couple of transformations here, x minus 1 and plus 4. So for reference, the logarithmic one has reference point 1, 0 with a vertical asymptote at the y-axis. So essentially what we're looking here is this change right here, which is the horizontal change, will change the vertical asymptote. This will shift the graph up. Right. So now because it is moved to the right, the asymptotes will be at 1 here. And yeah, the reference point is going to be plus 4, right? So it's going to be 2, 4, right? So something like this. And then you'll have this. Okay? Okay. So I think that's about it for the graphing. So let's go to the systems of linear equations. So let's see, systems of equations is a set of 2 or more equations containing 2 or more variables. Well, for now it is. And to solve a system of equations, find the ordered pair or triple that satisfies all the equations. This ordered pair or triple represents the intersection of 2 or more equations. So there's 3 ways for now. That is by graphing, substitution, or elimination. So these are the 3 ways that we know as of now. There are also other ways, which we're going to learn down the road. Systems can be consistent and independent. So that is basically we're classifying solutions here. So let's see what these mean. Consistent and independent. This is exactly one solution. So what does this actually look like? When there's one ordered pair that satisfies both equations, right? So let's see. This is what it looks like. We have our 2 equations here. Let me use a different color actually, it's easier to see. So I'm just going to do the graphs later. Next one we have is consistent and dependent. This is infinite solutions, and one solution depends on the other. Inconsistent is no solution. So what do these actually look like? Well, basically, when you have a system of equations, you can actually graph these, right? You can graph these systems of equations. So we have a graph here. Just see. So graphs, use green. Okay. So when you have a consistent and an independent one, basically you have one equation here and maybe another here, and you see where they intersect as a single point. And that single point, that is the solution. Okay, but when you have consistent and dependent, then you have something like this. This is one line, and this is the other line. Meaning that these lines are exactly the same lines. These lines are the same. They have the same slope, and they are the same. They overlap is one, right? then that means they intersect an infinite amount of times. And how many intersections is how many solutions you have. That means you have infinite solutions. And you'll see an example of that later. What is inconsistent? Inconsistent is basically when you see these two lines, they are parallel. They have the same slope, but they have different intercepts. So they actually never intersect. And when you have no intersections, you have no solutions, right? Okay. So that is basically systems of equations. Substitution is now let's go over to some substitution examples. So I'm just gonna get a couple equations here and have you solve them. All right, so these two examples, I'll give you a couple moments to solve those. Okay, so let's see how you solve this. So yeah, Okay, let's see. Do I have any volunteers? How about William? Solve the first one.
Okay, so I so basically in order to substitute, oh wait, so that's a 3, right?
Yeah.
Oh, okay, so to substitute the y, I to use substitution, I just used move 2x to the other side on the second equation, so y equals 2x negative 2x plus 1. And after that, I plug negative 2x plus 1 into the y in the first equation, so it became 3x minus negative 8 y,
Okay.
so it became 3x minus 4, yeah, equals 18, and 3x minus 4 plus 8x equals 18.
Okay.
So then 11x equals 11x plus 4 equals 18. So oh wait, no, it's so it's
Now
so
plus.
it's so it's
Now plus.
11x equals 22,
There we go. That's
and
it.
then x equals 2.
And y is going to be equal to 3.
Uh,
Negative.
yeah.
6. Okay, so that was pretty easy. Not very important, right? You already know that. But now let's look at the interesting part. Now let's look at this one. All right, so William, can you solve this one then? Using like the same
Okay.
method.
Okay. So wait, can I use elimination for this one? Because like this, it's kind of easier to do it.
Yeah. Use elimination. I don't really
Okay.
care. I just
So
want to do it, yeah.
So then, on the second equation, I added it to be negative 2x, um, negative 2x, plus 4y is equal to negative 6.
Wait, hold on.
And then,
You can just add it like this actually.
oh yeah, then you just add the equations and it becomes 0 plus 0 equals 0, and that's infinite solutions.
Yeah. So actually once you get to this point, 0 is equal to 0, what you can do is, since you can use the substitution, since you have infinite solutions, then you have to set parameters. Okay. So set parameters. Since x is equal to 2y plus 3, you gotta have 2s plus 3 and then s. Okay. Well, s can be equal to any number, right? All right. So that's how you set parameters. And we'll learn more about this when we go into matrices, so don't actually like worry too much about it. So let's go on to elimination. So let's actually just do sum here. Maybe like 7x plus 3y is equal to 5, and 2/3 x plus 4 over 3y is equal to 1. Let's just do these two, and I'll give you a couple moments to do that. Okay. Okay, so let's go over these. All right. So for elimination, what you have to do, right? You already know what elimination is, right? Because we learned this in our last class on basic algebra. So let's since I don't think we have too much time, right? We still have a lot of material to cover. So let's just pick one. Let's pick one. How about the right one, which involves fractions? So let's also review some fractions. Let's pick this one. 7x plus 3y is equal to 5. 2/3 x plus 4/3 y is equal to 1. All right. So let's see here what we get. What you have to do is get rid of the fraction, right? 2/3 and 4/3. What you have to do is you have to multiply everything by 3. So multiply this by 3. Okay. And what you get is 2x plus 4y is equal to 3. Right, because you multiply everything by 3. Now you have 7x plus 3y is equal to 5. So what you can do is you can subtract one equation from the other, right? So this one is not very good because none of them match up. The purpose of elimination is basically getting rid of one variable, right? Getting one variable by subtracting the fractions. And yeah, but right now we can't do that because none of these match up. So what you have to do is you have to find the least common multiple. Okay, so what you can do is you can multiply everything, this one by 3, for example. Maybe multiply this by -3, and maybe multiply this by 4. So then you have -12y and 12y. So when you add them, they cancel out. So -6x minus 12y is equal to -9. And this is 28x plus 12y is equal to 20. So now when you add these cancel out, right? And you don't want the y, you just want the x. So what you do here is now when you add it, you have 22x is equal to plus 0y, of course, because they cancel out, is equal to 11. So x is obviously equal to 1/2, and then you can go from there. So let's plug 1/2 into the first equation. It's equal to 5. There's 7/2 plus 3y is equal to 5. 3y is equal to what? 2.5. Y is equal to 2.5 over 3, which is something that I do not know. What is 5 again? It is, hold up. No, it's
Wait,
just 5.
isn't 3y equal to 1.5?
Oh, yeah, it's 1.5. 1.5. So it's also equal to, yeah, this is 3 over 2, actually. Again, also equal to 1/2. Right, something like that. Okay, so that's elimination, and that was pretty tedious, right? But I think it was the best option here, or maybe substitution. Substitution would be pretty nasty. So always use like the best method. So don't force yourself to use substitution or elimination, and definitely do not graph the systems and actually find the intersection, because that never works when you get onto like some fraction solutions. Okay, so now let's go on to 3 equation systems, and let's look at some of the things you can have here. So, for example, when you have 3 equations, they must all, basically 3 equations are planes, right? When you have systems of 3 equations, you have planes intersecting. So, let me just try to draw this. If not, I can always just hold up. I'm very bad at drawing this type of stuff, but Yeah, it's quite confusing. Okay. Yeah, that does not work. Okay, yeah, basically, so you know what a plane is, right? A plane is basically coordinate grid, x, y here. And basically when you have three equations in the system, you want all these planes to intercept at a one point. So basically on an XY dimension, it looks like this, right? But that's not actually what's happening because it's on a 3D dimension because there's three equations, therefore three dimensions. But on a 2D way, it kind of looks like this. You can also have no solutions, which is like this. This is no solutions. This is also no solutions because they do not intercept at one single point, and it has to intercept at one single point. Also, something like a triangle, like this, intercepts at three different points. So that also has no solutions. So make sure this is solution, this is no solution. Right, self-explanatory. Okay, so yeah, intercepting at one point. Okay, so now if we solve an equation of a system of three equations, it's going to be very difficult. Why? Because there's a bunch of variables. And we don't really know what to do to start with. Well, we do know what to do, but it's going to be quite tedious, right? It's going to be very tedious. So let's just solve one, right? And I'll give you like 5 minutes to do this because this one is quite complicated. So that's a z, by the way. So I'd rather you write your z's with a line. That's what most mathematicians do because sometimes it is confused with the 2. If you write 2 and then z like this, it looks like 22. So you write the z with the line inside. So I think this is correct. There's a solution to this. Yeah, this is a one solution problem, I think. All right. Yeah. Okay. So solve this one. And systems are usually indicated with this bracket. All right, so I think it's been a couple of minutes, so let's go over this. Okay. So let's see here. 5x plus 3y plus 2z is equal to 2. And let's see which is the best to mess with here, right? Which is the best to mess with? Well, as you can see, we already have two z's here, two z's. And that's very nice, because what we can do is we can take equation 3 here. We can take equation 3 and minus equation 1. Right? So equation 3 minus equation 1 is what? It is going to be, let's see, negative 4x, right? Negative 4x. And plus y, and that is no z's, right? This is 14. Okay, so that is 3 minus 1. So now we have equation with two variables. Now we need to get another equation like that. So what we can do is we can add, I think 2 and 3. So let's multiply. Basically multiply equation 2 by 2. 2 times equation 2 plus 3. And this is basically the beginnings of matrices actually, like matrix manipulation. That's what it's called. So you have 4x plus 2y minus 2z here is equal to 5. And x plus 4y plus 2z here is equal to 16. And then when you add them, you get 5x plus 6y is equal to 21. So now you can actually find x and y. Right? All right. So what should we do here? We can take the 1y here and subtract it like that. Right? So let's see here. Multiply this by negative 6. This is going to be equal to 24x minus 6y is equal to negative 84. This is quite annoying. Of course, I hate doing this because it's very complicated and messy. So I hate the 3 equation systems like this, but it will be much easier with matrices. It's much more organized and you can do a lot of stuff with it. So now you have 29x is equal to negative 58. No, I don't think that's correct. What happened here? Okay. So let's see. All right. Apparently if you do this, it's going to be negative 63, which is not what it is. So what happened here? 29x is equal to, yeah. I don't think I did it correctly. Let's try to find what happened. All right. Okay, who can help me find what happened here? So let me see. First I did, wait, did I even copy this correctly? The problem, is the problem correct? Yes, the problem is correct. So let's see what we did here. So if you take 3 minus 1, we are going to have, right, that makes sense, that makes sense. And yeah, negative 4x plus y is equal to 14, yeah? Okay, so that's correct. And we multiplied this by negative 6. Okay. So, and then the next thing we did was multiply 2 times 2 plus the 3 to get our second equation. So, oh, yeah, that's where I went wrong. That's where I went wrong. So, this is 10. This is 26, actually. So yeah, so this is negative 58 and x is equal to negative 2. Okay, so now there's x is equal to negative 2. We can now find y. S is equal to negative 2, we plug it in, right? And y is equal to 6. We plug it into this, y is equal to 6, and if we plug into whatever else, so negative 10 plus 18 plus 2z is equal to 2. It's quite obvious. It's going to be negative 3. So as you can see, my work is very complicated and not very organized, right? First of all, I didn't have much more space, but as you go on with 3 equation systems and maybe 4 equation systems, you'll realize it's a very bad way to like solve the system. Just by algebraically, it's going to be quite complicated. So that's why we introduce matrices when we're solving big equations like that, right? So this is all about using matrices to solve the systems, and we'll learn about matrices here in a couple of lessons. So yeah. Okay, are there any questions? If there are no questions, then that's it for this class, and I'll post the recording and the homework very soon. All right, I'll see you guys, and see you next time.